Okay, in this video, we're going to talk a little bit about higher order derivatives. Basically, the concept of being able to take a derivative of a regular function applies to itself as well. So if we have our parent function of f of x or y equals whatever it ends up being, our first derivative we've learned how to take. And the symbolic notation, we've got a y prime or an f prime of x. Or dy dx. There's a variety of ways of noting this. However, we can take that derivative and take a derivative of it. And this is called the second derivative. And the notation is very similar. Instead of a single prime, we've got two primes. So it'll be y double prime, f double prime of x, d squared of y over dx, or d squared y over dx squared. There's a variety of ways of writing that. Speaking it sometimes is a little more difficult than actually writing the notation. Needless to say, all of these represent the second derivative of a function. And that continues on to the third and the fourth and fifth, and really as long as you can possibly do it on the function that you're being asked to take the derivative of. I've never seen something where we've gone to the fourth or fifth derivative, at least not in my limited experience. But third is not very uncommon. So the way that this works is we would basically take our first derivative, and the function we get from that, we would take the derivative of that. That would become our second derivative. The function we take of that would then become our third derivative. And so if we have our f of x, that gives us our f prime of x. If we have the first derivative and we're asked to take the derivative of that, then we get our f double prime of x, or our y double prime, or however you want to denote this. If we have our f double prime of x, that can be the derivative of that becomes f triple prime of x, and this goes on and on and on until you decide to stop. So let's take a look at an example here. In this case, we've got a function f of x is equal to 1 over 2 times the cube root of x squared. Well, that's a pretty cool function. It looks pretty nice and ugly, maybe. But let's make this look a little bit nicer. Okay, remember, one of the first things we want to do in order to use the power rule is we got to put it into a power form. And so this becomes 1/2. That's our constant here. So 1/2 times, now this cube root of x squared can be written as the x to the 2/3 negative. And the negative has to be there because that's what tells you it's in the denominator. So we've got it in our power form. The first thing we're going to do is go ahead and look at our f prime, our first derivative. Okay, and so this is going to be 1/2. The power form says that our power rule says that we we bring our 2/3, so 2 over 3 down, and this becomes x, and then the value is, the power value is subtracted by 1. So this ends up becoming a -5 over 3. Okay, and that simplifies out so that our first derivative of x is equal to 1/2 times 2. Let's see, that would be 1/3, a -1/3. Sorry, multiplying the 2/3 and the 1/2 together, -1/3 times x to the -5 over 3. Now, in this case, they've asked us to go ahead and run a number 1 through it. And so if we ran the number 1 through it, this would be f prime of x, not x, the f prime of 1. And we would plug that into the function, which is a -1/3 times 1 to the -5/3. When we plug this in, 1 to all of this is going to still give us 1. That's a nice one. And so this ends up becoming just simply -1/3. Now, our double prime here is a little bit more exciting. And in this case, we need to take the derivative of this first derivative. So our second derivative is the derivative of the first derivative. So if we're looking for that, this is our f double prime of x is equal to, now we've got the negative 1/3. We're going to leave that out in front. And we've got to deal with this x to the negative 5/3. Well, to do that, we take out our negative 5/3. That becomes x, and we subtract another 1 from that. So this now becomes a negative 8/3. And that's our second derivative. We can go ahead and solve the constant through, the scalar part through. This ends up becoming positive 5/6, no, 5 over, oh, I'm not sure where I came up with this 1/2. This is supposed to be 1/3. Sorry, so 3 times 3 would be 5/9. That makes things a little bit nicer. And then x to the negative 8/3. And that is our second derivative of our function there. Now we've been asked to plug in the value. In this case, that's going to be kind of a fun one, and I would definitely need a calculator for that. And so our value is a negative 8, and then to the negative 8/3. We can go ahead and leave it like this, because this would be the exact form rather than putting it in decimal form. You may be able to simplify it just a little bit. The negative 8 could be negative 2 cubed. So this could be also written as 5/9 times a negative 2 cubed to the negative 8/3. These cubes, when you're multiplying powers, this would be 3 times negative 8/3. Those 3's end up canceling out, and it really could be written, perhaps the simplest form that you can get without the calculator would be 5/9 times negative 2 to the negative 8th power.